I need to do the work on the assignments. Yes, was teaching today for the summer school, and then I was doing some work in the morning. And so back to back 3 hour lectures on 2 consecutive days leaves me absolutely no time to do anything. But right, I am not sure that I have 3 hours of material today. But we'll see. So I will do some work and then update you on the status of the assignments tonight after this. And I don't have a course website at the moment. I need to do that as well. But again, 3 hour lectures a week. This is slightly excessive because I'm also teaching another summer school. And yeah. And I need to send you the recordings as well. Okay, I can write this down. So I can send you, you should have received the first 2 recordings, right? So you need the next 2 recordings. And notes, and assignment stuff. Okay. Right, so let's get started. So we're back to talking about second order ODEs. But let's remember something that we did for first order ODEs. So for first order, linear ODEs. For first order linear ODEs, recall. For the equation y prime is equal to f of x y plus f of x y is equal to g of x. We had 2 methods for solving this. The second one was the method of undetermined coefficients. And what we said is suppose that y1 is a solution of the homogeneous system. Then what we did is then we use the ansatz of y is equal to u y1, where u is an unknown function. So what we're going to do for second order systems is precisely the same thing. So if we know 2 solutions of the homogeneous equation, and the equation that we're considering is y prime prime plus f of x y prime plus g of x, y is equal to h of x. So if y1 and y2 are solutions of y prime prime plus f y prime plus g y is equal to 0, then what ansatz shall we use?
Maybe like u times y1 plus v times y2.
Sure, let's call them u1 and u2. Good. So what we're going to do is have two unknown functions. Now, in general, we're trying to solve the equation that's when we plug y inside of here, we have h. So that is one constraint, whereas we have 2 degrees of freedom for the functions here. And this will allow us to impose an extra equation to make the solution possible. So what we're going to do is we are going to say, well, suppose this is y. Well, then what is y prime? So I get chain rule and I get terms. And at first I'm going to differentiate the u's. So I'll get u1 prime y1 plus u2 prime y2. But then as a result, I'll also get the terms in which I differentiate y. So u1 y1 prime plus u2 y2 prime. And what we're going to say is that we don't like this term, actually. So because we have 2 equations, because we have 2 degrees of freedom and 1 constraint, what I'm going to say is we will search for solutions in which this is 0. And so this is going to be an important equation. And at the moment, I'm allowed to impose whatever equations I want. If I can impose 100 equations, but then it's probably going to be impossible to find a solution to the system. But I'm going to claim that when we impose this equation, we'll actually are going to be able to solve for u1 and u2 uniquely up to a constant, additive constant. Now, okay, if we have that, then we're going to differentiate this again. And now this term is 0, so we're only differentiating this. And what we get as a result is that u1 y1 prime prime plus u2 y2 prime prime plus, and then I get the terms where I differentiate u1. Okay, so I know what y prime is and I know what y prime prime is. So now I plug everything in to the equation. So the equation is y prime prime plus f y prime plus g y. And what I'm going to get is that I'm going to keep these terms at the very end. So first I'll just write these terms and then I'll write the u1 terms first. So I get u1 y1 prime prime. Then I get the u1 term from here plus f or u1 times f y1 prime. And then I get the u1 term from here plus, and then this is u1 y1. So it's u1 g y1. Then I get the next same terms for u2 and y2. And then I have these terms right here. So they are additional terms. And so I get plus u1 prime y1 prime plus u2 prime y2 prime. Now, what can you tell me about this collection of terms and that collection of terms? So I can rewrite it. I can factor u1 out.
Oh, we know there's 0.
Yep, because this is exactly the equation that y1 satisfies. So these terms are 0. And so as a consequence, we get 2 equations. In summary, we have the equation that we imposed, which is u1 prime y1 plus u2 prime y2 is equal to 0. And then the other equation that we have is that if we look at this expression, then it's equal to this. But we want to solve the equation, this is equal to h of x. Because we're supposing that y, what we're constructing, this is an ansatz for the solution of the inhomogeneous equation. So this expression right here is equal to h. And what I can do is I can take this system of equations and I can rewrite it as a matrix multiplication problem. So I can consider the matrix y1, y2,
Sorry.
y1 prime, y2 prime. That's not a square, that's a 2. And the vector u1 prime, u2 prime. And this gets sent to 0 and h. Now, the way that matrix multiplication works is that you do, in general, if you have this and then you have this, you do, I guess I do it like this, So you do this with this to get that entry. So the ijth entry is given by the product of the ith row of the first matrix with the jth column of the second matrix. So in particular, this says that y1 times u1 prime plus y2 times u2 prime is equal to 0, and y1 times y1 prime times u1 prime plus y2 prime times u2 prime is equal to h. So that's exactly the way to write this. Now, there is a fun fact about inverting 2x2 matrices. 2x2 matrices are very easy to invert. So if you have a matrix A, B, C, D, does anyone know the trick for inverting a 2x2 matrix?
Is it like D minus B on the first row and then
So what goes in the top entry?
like the
left?
diagonals flip. Oh no,
Yeah,
no.
the diagonal flips.
And then the other one's negative.
Exactly. And in order to make this true, you have to divide by something. What do you have to divide by?
The determinant.
Yes. So in particular, if the determinant is 0, then this formula does not make sense. So this exists if and only if a d minus bc is equal to 0. But in our case, in our example, the determinant of the matrix is the Wronskian. Exactly. And if y1 and y2 are linearly independent, then the Wronskian is never 0. Because it's an exponential, because we calculated it last time from a differential equation. Then the Wronskian is never 0. So it is possible to invert the matrix so long as we choose two linearly independent solutions. And so never in this analysis did we actually assume that y1 and y2 were linearly independent. Well, the problem is that if we don't assume that they're linearly independent, then we're not actually able to solve for u1 and u1 prime and u2 prime. But if they are linearly independent, then this matrix is invertible. And so we do actually get an inverse. And so as a consequence, what happens is that u1 prime, u2 prime is equal to the inverse of this matrix. So that matrix is y1, y2, y1 prime, y2 prime inverse times 0h. And so we get the 1 over the determinant times swap the diagonal, put a minus sign here. And then 0 in h. And as a consequence, then we do this. So we're going to multiply this by this to get the top entry. And so we get 1 over this expression, the Wronskian. And then as this entry, well, we have 0 times this, so that's just 0. And then we have h times this. So it's minus y2 times h. And here we're going to have y1 times h. So as a consequence, using these linear algebra facts, the takeaway is that u1 prime is equal to negative y2h, and u2 prime is equal to y1 of h. So the first equation gets a negative sign, the second one does not, and we swap y2 with y1 when doing u1 and u2. But this in particular, this is just a function of x. So this is a set of differential equations for u1 and u2, which are what?
Oh, separate.
Yes. So as a result, we're able to solve for u1 and u2. U1 is equal to negative the integral of y2 h. Well, I can, I guess, write the x in. And then I can add in the constants, and let's see what the constants mean. No negative sign. And now let's remember what y is. So it's equal to, well, let's look, so these terms, ignoring the constants, we get negative y1 times the integral of y2 x h x z x plus y2 times the integral of y1 x hx. And then let's look at what C and D give us. Then we get C times y1 plus D times y2. And this is very good because C and D are solutions of the homogeneous equation. So if we add any multiple of them, then the left-hand side of the differential equation sends them to 0. So in general, we can add any multiple of the solutions of the homogeneous equation to the inhomogeneous equation. So the constants exactly account for that. And U1 and U2 are defined as to solve the system. So we're able to solve for U1 and U2 uniquely so long as we've chosen linearly independent Y1 and Y2. And so this gives you a process for if you know the solutions to the homogeneous equation, then you know the solution you can find the general solution of the inhomogeneous equation. And the idea was, well, for first order systems, the second technique that we used was this ansatz, and we're just going to use a similar ansatz, except we're also going to impose an extra condition. So let's do some examples. So let's look at an equation like y1, sorry, y prime prime plus y is equal to 1 over cosine cubed of x. So we start off by solving the homogeneous equation. So what polynomial do we consider?
Gamma squared plus 1 equals 0.
Yes, and the roots of this are
Plus and minus I.
and so we get solutions. Get y1 is equal to what? What's one of the particular solutions?
Oh, cos.
And then the other solution, so we're going to separate it into two solutions, is
just sine.
yeah.
Oh.
So we don't want to write down the general solution. We just want to write down two linearly independent solutions so that we can use our ansatz. So then use the ansatz that y is equal to u1 cos x plus u2 sine x. And I'm going to require you in your solution to write the hypothesis that we're assuming, such that u1 prime cos x plus u2 prime sine x. 1 second. Let me just see if I'm writing the right thing. The thing that we're assuming is 0 is this expression with the original things. Yeah. Then And now we can use our formulas. We can use the expression for U1 prime. Actually, before I do that, then note that we calculate what the Wronskian is. Y1 times Y2 prime minus Y1 prime Y2. What is that equal to?
Sine squared minus cosine squared.
Well, let's see. For y, when we get cosine, the derivative of sine is cosine, so we get cosine squared.
Oh, it's 1.
Yes, so here we get plus sine squared x. And by Pythagoras, that's equal to 1, because these points all lie on the unit circle. Right. So we have, and now we memorize what the formulas are. So U1 prime is negative Y2H and U2 prime is Y1H. That's what we remember. Is equal to, sorry, this is incorrect. These are incorrect formulas. They're divided by the Wronskian. Yeah, there's a Wronskian factor here. Whoops, that is a bit annoying. I'll write divided by W, 1 over W. Okay, that fixes it. So we have U1 prime is negative 1 over Wronskian, which is 1. And then it's negative, and then we have Y2, which is sine x, times H, which is 1 over cosine cubed x. And U2 prime is equal to just 1 over the Wronskian times Y1, which is cos x, times 1 over cosine cubed x. So here we get, we can write this as negative tan x secant squared x. And this we can write as secant squared x. And these are actually pretty not bad integrals. So U1 is equal to negative the integral of tan x secant squared x dx. And what substitution do we make?
Tan x.
And what's the derivative of tan?
The secant squared.
Yep. So this equation just becomes negative integral u du, which is negative 1/2 u squared plus c, which is negative 1/2 tan squared x plus c. And u2 is solved by inspection. Secant squared is the derivative of tan. And then I'm going to name my constants C and D. Thus, y is equal to, well, u1 times what is y1? My y1 is cos x. So I get -1/2 tan is sine squared over cosine squared, and I'm multiplying by cosine. So I get sine squared x divided by cosine x. And then here I have sine over cosine, and I'm multiplying by sine. So these two terms combine, and then I get my c times cosine x plus d times sine x. So I always first do the non-constant terms, and then I throw in the constants at the end. And so this simplifies to just 1/2 sine squared. Or I can write that as tan times secant. No, tan times sine. So we are now able to solve inhomogeneous second order differential equations. And if there's constant coefficients, we can solve the homogeneous system always, because that's just solving a polynomial. Okay, let's do another example. So let's consider y prime prime minus y is equal to, is that different from the equation? Yes, it's different from the equation that we were considering before. 2 over e to the x plus 1. And so what we get is, consider y prime prime plus y minus y is equal to 0. So we consider lambda squared minus 1, which factors as lambda minus 1 times lambda plus 1. So this, and we get y1 is equal to what?
E to the x?
Yeah, and then the other one would be e to the negative x. Right. So now what we're going to do is use the ansatz that y is equal to u1 e to the x plus u2 e to the negative x with the constraints that u1 prime e to the x plus u2 prime e to the negative x is equal to 0. Then for write w is equal to y1 y2 prime minus y1 prime y2. What we get is e to the x times this derivative, which brings out a negative sign. And then minus this derivative, which is just e to the x. So both of these are 1, and so we get -2 as the Wronskian. And they shouldn't cancel out because they're linearly independent solutions. So we made a mistake if they cancel out, but they don't. That's a number, that's not 0, so it's good. Well, then what u1 prime is equal to is that it's 1 over the Wronskian, -1 over the Wronskian, -2 of y2 times h, and h is 2 over e to the x plus 1. So overall, what we get is the 2's cancel out, the negative signs cancel out. We get e to the negative x over e to the x plus 1. But we can rewrite this in a nice way. Let's say that we considered e to the x plus 1 times e to the negative x. Then what would I have to write here to make this equation true?
-1.
Or rather, I have the negative e, I have one, I have, yeah, -1. That's right. And so what that gives me then is that it's e to the negative x minus 1 over e to the x plus 1. However, I'm going to do something even more clever. I'm going to divide top and bottom of this by e to the x. So I'm going to write this as e to the negative x. Then if I divide this by e to the x, I get 1. And here I'll have e to the negative x. So the reason that I manipulated it like this is because this is a quotient where the derivative of the bottom is equal to the top, right? So that's going to make it easy to integrate. And u2 is equal to 1 over the Wronskian times y1, which is e to the x, times this fraction, which is 2 over e to the x plus x. So that's negative e to the x over, sorry, that's a plus 1. I see. That's where that negative sign came from. Okay. I'm pretty sure my notes have a negative sign error then. Well, what we can rewrite this as is minus e to the x plus 1 minus 1 over e to the x plus 1. And so this is equal to minus 1 plus 1 over e to the x plus 1. And as a consequence, what we have, and then I should, sorry, this is u2 prime. Actually, I do not want to do it like that. I do actually want to keep it like this because the derivative of the bottom is now minus the top. This is better to integrate. So u1 is equal to, well, we're integrating e to the negative x plus negative e to the negative x over 1 plus e to the x. And so what we get for the first expression is just negative e to the negative x. And here we notice that the derivative of the bottom is the top. So that's going to give us a logarithm of, sorry, this is negative x. 1 plus e to the minus x plus c. And u2 is going to be, well, we notice that this is negative the integral e to the x over e to the x plus 1 dx, and that the derivative of the bottom is the top. So this is negative logarithm e to the x plus 1, or I can write it symmetrically with the previous one, plus d. That's a c. And so as a consequence, what we get is that y is equal to u1 y1 plus u2 y2. And that is equal to, well, let's see, u1 is e to the x. So I'll get negative 1 plus e to the x times logarithm of 1 plus e to the minus x. Then I'll get, so this is e to the minus x minus e to the minus x logarithm 1 plus e to the x. And then I'll get plus c. I guess I can write that in that line. Plus d e to the minus x. So that solves that problem. And I think there is maybe a bit of manipulation that you can do here, but it's not strictly necessary. Now let's do another problem. Let's do y is equal to, no, let's do something interesting. X squared y prime prime plus x y prime minus y is equal to 4x squared e to the x. So if we consider the homogeneous equation, the equation x squared y prime prime plus x y prime minus y is equal to 0 is what kind of equation?
U.
Yes, Euler. So we consider, well, we subtract the first coefficient from the second one. Lambda squared, then this becomes 0. And then this is minus 1. And that's lambda minus 1 times lambda plus 1. And gets particular solutions. Y1 is equal to what? So these are going to now be exponents on polynomials. So it's going to be x to the first power and x to the negative first power. So if we remember what's the method for writing down the solution was from last time. So use the onslots that y is equal to u1x plus u2x inverse. And with the constraints, u1 prime x plus u2 prime x inverse is equal to 0. So with this, then we have, so the Wronskian, we need that to write down the solutions. Well, y1 is x, and the derivative of negative x inverse is negative 1 over x squared. And then if I take minus the derivative of x, then that's just 1. Then I get divided by times y2 x. So that's negative 2 over x overall. And here is the very tricky part in which you're almost certainly going to make a mistake. This equation is not of the form y prime prime plus stuff. There is an x squared out front. So what we're going to have to do is we're going to actually have to remember that h is defined in terms of equations in which this is 1. So we're going to need to divide this by x squared in order to get h. So for this equation, which is the same as y prime prime plus 1 over x y prime minus 1 over x squared y is equal to 4 e to the x. H is equal to 4 e to the x, not 4x squared e to the x. And u1 prime is equal to negative 1 over the Wronskian times y2, which is 1 over x, times 4 e to the x. And so this x comes up top, it cancels with this x here. So we get this 2 cancels with this. So 2 e to the x. And u2 prime is equal to 1 over the Wronskian times y1, which is x in this case, times 4 e to the x, which gives me a negative sign, negative 2x squared e to the x. And so u1 is equal to the integral of this, which is just 2 e to the x plus c. And u2 is equal to negative 2 times the integral of x squared e to the x dx. And how do I do this integral?
Integration by parts.
And what do I want to differentiate? What am I differentiating?
X squared.
Good. So df is 2x dx. And g, well, if I integrate e to the x, I just get e to the x. So I'm going to keep this minus 2 out front. And then I'm going to get the cross term, x squared e to the x, minus the integral of 2x e to the x. And then I do parts again. So now I'm going to differentiate x. So that's minus 2 times x squared e to the x minus 2 times, now I get the cross term x e to the x. And then I get minus integral e to the x dx, which is just going to be e to the x. But now I'm going to expand out everything. So I'm going to get minus 2 times this. So it's minus 2x squared e to the x. Then it's going to be plus 4 x e to the x. And then this is going to be, there are now 3 minus signs. So minus 4 e to the x. Plus I put a c there, so I put a d here. Okay, so what do we get as a result? We get that y is equal to u1y1 plus u2y2. And that's going to equal, u1 is x, y1 is x, y2 is x inverse. So this times x, 2x e to the x. And then we get this times 1 over x. So minus 2x e to the x plus 4 e to the x minus 4x inverse e to the x, then plus cx plus d x inverse. And that is, these two terms cancel out, 4 e to the x minus 4 x inverse e to the x plus c of x plus d of x inverse. So we can even solve, if we can solve the homogeneous problem, then we're good. The very important thing and the very easy mistake to make is that the methods that I explained apply when this coefficient is 1. So if it's not 1, you have to remember to divide through. And so now is an excellent time for a break, and we will take a 15-minute break until 7:10. Okay, hey. Yeah, I am going to end the lecture an hour early today because I have not had enough time to prepare 3 hours of material with the other teaching commitments and something that I need to prepare for Friday. But we'll see what we can do. So there's another thing that I'm going to talk about now, which is a second method of solving inhomogeneous equations, which is sometimes easier, and it works when the equations are of a special form. And this is called the method of undetermined coefficients. So in this method, what we're going to do is we're going to look at constant coefficients, linear homogeneous equations. Constant coefficient linear equations. So let's say ay prime prime plus by prime plus c is equal to h for h something simple. For h is equal to, let's say, some constant d times e to the tx. So if it's something very simple, then we're going to be able to find things basically by special cases. So instead of going through this very long process that we saw above, in certain cases, we'll just be able to do it, and I'll tell you when it works in general. Case one. And usually they cover this method before they cover the other method. But I thought it would be good to do the general method first and then just do some special cases which can be easily solved later. So case one is going to be that h is equal to d times e to the tx for t not a root of a lambda squared plus b lambda plus c is equal to 0. So what happens is that basically we considered what happens when we have the ansatz. U is equal to a times t to the x. So we're going to use the ansatz. Y is equal to a e to the tx. So when we use this ansatz and when we plug this into this equation, we get what we saw before. A y prime prime plus b y prime plus c y becomes, so we're going to get a out front, and then we're going to get a t squared plus b t plus c e to the tx, right? And what we'd like for this to equal is d e to the tx. Thus, a is equal to d divided by this, the characteristic polynomial evaluated at t. And this only works when this isn't 0, of course. So let's do an example. Or I can tell you, okay, I guess I can tell you what the other cases are. Case 2 and 3. So basically, if t is a simple root, means that it has multiplicity 1, use y is equal to a times x e to the tx. And if t is a double root, use y is equal to a x squared e to the tx. And you can verify that what will happen is that if it's roots, okay, so let's see what happens. If a lambda squared plus b lambda plus c is equal to, let's say, let's imagine that a is 0 for the moment. Or rather, I'll keep it out front. Let's say this is equal to a times lambda minus t times lambda minus s for t does not equal to s. Then a y prime prime plus b y prime plus c y can be rewritten as saying a times d minus t times d minus s applied to y. And where d is the differential operator. Now, so if, let's write it like this, so that the t1 is applying first. We saw this trick of factoring this, and we claimed that this factorization makes sense. So if t is, if we apply d minus t to x e to the tx, then what we get as a result is, well, when we differentiate this, we get e to the tx plus tx e to the tx, and then we get minus t times this. So that's just equal to e to the tx. And then the hypothesis was that t is not a root of s. T and s are distinct. Then d, I guess, minus s of e to the tx is going to equal t e to the tx minus s e to the tx, which is t minus s e to the tx. And this is a non-zero multiple of e to the x. And what we want is, we want, when we apply this differential operator onto this, we want to get some multiple of e to the tx. So in the case of a single root, the ansatz x e to the tx will always work. And in the case of a double root, well, so d minus t squared x squared e to the tx, you can verify that this is going to give you, well, let's just do it. So this is d minus t of, well, let's say we differentiate this, so we get 2x e to the tx plus t x squared e to the tx minus t x squared e to the tx. So that's d minus t times 2x e to the tx. And we've already done the previous example. That's just going to be 2 e to the tx. So in both cases, if we apply our differential operator to something of the form x e to the tx or x squared e to the tx, then we get some non-zero multiple of the thing that we want to have a non-zero multiple of, and then we just adjust the coefficient so that it works. Okay, examples. So let's say we have something like y prime prime minus 4y prime plus 3y is equal to 24 e to the negative x. Then what we consider is for lambda squared minus 4 lambda plus 3, we can factor this as what?
Lambda minus 3 times lambda minus 1.
And in particular, this root is not minus 1. This root is 1. So this root is not negative 1. So this negative 1 is not a root of this equation. And as a result, we're going to use the ansatz that y is equal to a times e to the negative x. Then y prime prime minus 4y prime plus 3y becomes a times, and then I can just write down the polynomial because I'm going to evaluate the polynomial at negative 1. So it's going to be negative 1 squared minus 4 times negative 1 plus 3. Yeah, and in particular, all of these coefficients are actually positive. E to the negative x, and we want that to equal to 24 e to the negative x. So what we get as a result is that 8a is equal to 24. So a is 3. And now we want to write down the general solution to this system, right? So we have found using our ansatz a particular solution. But what is the general solution? So let's write down our particular solution. It's 3 e to the negative x, and then I write plus c times what?
Times the homogeneous.
Yeah, well, what's the solution to the homogeneous equation?
E squared, oh yeah, e to the 2x.
Where did 2 come from? What
Oh,
are
free x. Free x.
Yeah. Plus d times what?
E to the x.
Good. Right. So yeah. So in general, we always want to write down general solutions. So after you found a particular solution to the inhomogeneous problem, the general solution is that plus solutions to the homogeneous problem. Okay, and now let's consider a more interesting example. Let's consider the same polynomial, y prime prime minus 4y prime plus 3y, but now we're going to write not what we had before. Now we're going to write 8 times cosine of x. And so the question is what we did above enough to calculate it's when it's not e to the x, but when it's cosine x? So the equation is the same one from before. So we have lambda squared minus 4 lambda plus 3 is lambda minus 3 times lambda minus 1. And the key is that the cosine of x can be written as e to the ix plus e to the minus ix over 2. Or it can also be written as the real part of e to the ix. Right? Because the real part of alpha plus I beta is just defined to be alpha. And e to the ix is cos x plus I sine x. And it's actually this expression that we're going to use. That's the more useful one. So what we're going to do is we will solve for y prime prime minus 4y prime plus 3y is equal to 8 times e to the ix. And then we'll take the real parts. And then 8 cos x is equal to the real part of 8 e to the ix, which is equal to the real parts of y prime prime minus 4y prime plus 3y. And the key is that the coefficients of this equation are real. So the real part distributes over addition, and you can take real multiples out of it. So this is the same as the well, you can, and then it also commutes with differentiation. So this is going to be the same as real y prime prime minus 4 real y prime plus 3 real y. So real of y is a solution to our original equation. And it's interesting to say that the real part commutes with derivatives, but that's sort of clear because if you have a function that has a real part and an imaginary part, then the derivative takes the derivative of the real and imaginary part separately. And if you throw one of those away, derivative of a purely imaginary quantity isn't going to be a non-zero real quantity. So basically, we're going to now solve a different equation. We're going to solve the equation here, e to the ix, but I is not a root of this, right? So we're going to use the same approach as before. So ansatz, y is equal to a times e to the ix. Then y prime prime minus 4y plus 3y prime, 4y prime plus 3y becomes a times I squared minus 4I plus 3 e to the ix, right? And we want that to equal 8 e to the ix. So as a result, we get that a is equal to 8 divided by, so I squared is -1, so we get 2 minus 4i, which is 4 over 1 minus 2i. However, complex number, fractions with complex number in the denominator aren't easy to work with. And there's a trick for getting rid of that. What's the trick?
Multiply by conjugate.
Exactly. And the conjugate of 1 minus 2i is 1 plus 2i. So we're going to multiply top and bottom by 1 plus 2i. And what happens, it's the opposite of difference of squares factorization. It's sum of squares factorization. So here we'll get 4 plus 8i. And here we'll get 1 squared plus 2 squared, which is 5. So now we've turned this number, which has a complex thing in the denominator, into a standard complex number, which we can reason with. And so what happens is that y is equal to 4 plus 8i over 5 times e to the ix. But this function has both a real and an imaginary part. And so we can write this as 4 plus 8i over 5 times cos x plus I sine x. Now, instead of multiplying it out, I'll just write what the real part is so that I don't have to calculate the imaginary part. The real part is going to be real times real and imaginary times imaginary, because the other things are imaginary cross terms, right? So what we're going to get is 4/5 cos x, and then minus 8/5 sine x. And so the general solution is for y is equal to 4/5 cosine x minus 8/5 sine x. And then it's the same homogeneous equation. So we're going to have c e to the 3x plus d e to the x. So that's how you handle cosines and sines. And in general, this technique applies to some other things. You can also have like x squared cosine x. And then you can ask, well, how am I going to solve that? Well, there are techniques. And I didn't really prepare more examples of this. So there are special cases in which it's easier to solve. And this method is arguably more direct than the general method that always works that we saw before. Okay, now I'm going to make like a very, very contentious decision. Technically, what we did right now, it's very similar to higher order linear equations. So in particular, if you have a constant coefficient linear equation, you can probably see how that's going to work. We're going to have a polynomial of degree n, and then we're going to solve for it using the same onslaughts. And then we're going to get solutions of the form of exponentials. And if there are repeated roots, then we're going to multiply them by a suitable power of x, which is 1 less than a multiplicity of the roots. So that's how you solve homogeneous constant coefficients linear equations of arbitrary order. Okay, now you know about that. Now, what about the inhomogeneous equation? Suppose you can solve the homogeneous system. Well, then you use the method of undetermined coefficients. Sorry, the method of what did I call it? It's very so the first one is called it's not called undetermined coefficients. That's what we just did. It's called variation of parameters, which is we assume that for our particular solutions we have u1 y1 plus u2 y2 up to u2 yn. And then you're going to impose n minus 1 additional equations. And then there's going to be basically a linear algebra thing. And then you're going to invert a higher matrix. And then you're going to get what the solution to the homogeneous equation is. So it's basically the same theory that we covered. And I'm just not going to do it now. Instead, I'm going to move on to the next topic directly. Does anyone have any questions about the higher order theory? I'm not sure if I'll work it in later. Maybe I will, but in any case, I'm about to show you that that theory of higher order linear equations, it actually reduces to a more general problem that I'm about to show you. And so we're going to move on to the topic of systems of ODEs. And so this is going to be the section of the course where we're going to use a lot of linear algebra, and we're going to have to work with matrices, and we're going to have to invert general matrices, and we're going to have to solve for eigenvalues, etc. And this is all part of the course material. And it's just, you just learn how to do it. So I'll tell you what a first order ODE system is. So there are going to be m unknown equations. The equations are going to be y1 through to ym. And we're going to say what their derivatives are. So their derivatives, well, they're going to depend on what x is. Then they're going to depend on all of the values. That these take. Sorry, that's y1. And so in general, you can see what a higher order system would be. In a higher order system, we're going to have the same order of derivative here. Let's say it's going to be an nth order system. And then this will depend on not only the values of y1 through ym, but also their derivatives up to one less than the order of the system. But in reality, we're basically going to study first order ODE systems, and mostly those with constant coefficients as well. So now here's a reduction. Suppose we have a nth order ODE. And that equation is going to be y to the nth order is equal to f of x y through to y to the n minus first derivative. So this is what an arbitrary nth order equation is. Well, I'm going to claim that we can write it as a first order ODE system. Consider y1 prime is equal to y2, y2 prime is equal to y3, etc., up to y to the n minus 1 prime is equal to y to the n, and then y of n is equal to f. And now we have expressions for what all of the derivatives are. So f depends on x. It depends on y1. Then it depends on y1 prime, which is y2. And then it depends all the way up to y, the n minus first derivative, which is going to be yn. So what I've shown is that in general, all nth order ODEs can be expressed as a first order system with n equations. So ODE systems present a very powerful reduction that we can do. And what we're going to work with in particular is linear first order systems. So what a linear first order system with m equations looks like is we have y1 prime is equal to, the coefficients are going to now be labeled as they would with matrix entries. And then let's use n. And then we're going to have the inhomogeneous part, which I'll call f1x. And then we're going to have a bunch of equations up to y to the n prime is equal to a. So here the second coefficient changes, here the first coefficient changes. And how we're going to express this is we're going to let capital A, which is a function of x, denote the matrix valued function A11 x, A1n x, AN1 x, ANN x. And then we're going to let f in vector style of x be this vector of f1 x through to fnx. So this is a vector valued function. Then for y vector form is equal to, and this is the unknown vector valued function that we want. The equation becomes that A times vector version of y plus vector version of f is equal to the derivative of this. And so this is an equation for the unknown vector valued function y. And let's see where we are. We are, okay, 45 minutes. Well, that's actually basically all that I have for today, except for the fact that I can do a few more examples and answer a few more questions. So I'm going to look up examples in an ODEs book that I have. And what we're going to do next time is we're going to talk about ODE systems. And this is going to begin with probably a bunch of linear algebra review slash not review. So can anyone actually confirm to me whether is linear algebra a prerequisite for this course of any kind?
It wasn't for me.
It wasn't. Okay. Then I'm not going to assume that you've seen any linear algebra before, and I haven't been assuming that you've seen any linear algebra before. I just said that you can put these things into a big box, right? That's what we're the level of formality we're at. Before I used inversion of 2x2 matrices. You know what? Actually, I may as well just talk about linear algebra, and this is going to be impromptu. So let's not do more examples. Let's just do some linear algebra. This is not going to be a very organized section, so we're going to start basically from scratch next time. So what happens is if you have a matrix like A11 plus up to, so first off, the first index indexes the row and the second one indexes the column. So this would be A1n. And then let's say it's an M by N matrix in general. So here we were considering square matrices, but here we're going to consider a more general case. So let's say that this is a M by N matrix. Then what happens is we can consider this and we can consider sort of multiplying it by another matrix. And I'll do matrix multiplication in general. So let's say we have a N by K matrix. And the entries are going to be B11 up to BN1. So this has to agree with that. And then we have B1K, and then we have BNK. Then the result is that when we multiply these, we're going to get another matrix. And that matrix is going to be an M by K matrix. And let's call the coefficients of this matrix C11 up to CM1, C1K, CMK. And how we compute Cij is that I is going to range from 1 to M, right? So it's going to index the I column here, which is going to have N numbers, right? And then we can consider the Jth row here. Sorry, the Jth row here. And this is also going to have N numbers, right? And so what we do is we multiply this by this, and then this by this, and then we add them together. And so we can write that as a sum. It's going to be the sum of, let's say, some third index, L, as that ranges from 1 to N, which is the dimension that isn't in the ranges of these. And then we're going to multiply by A. Well, the column here is fixed. It's the ith column times the elf entry times B. Well, the column now is going to vary. Yeah, so the column is going to vary. Sorry, the row is going to vary. Here, the column was varying and the row is fixed. And here, the first index is going to vary, and the second index will constantly be j. So basically, you're sort of contracting this index in all possible values and you're summing them together. So that's how matrix multiplication works. So I'm just going to write down a random matrix. So let's say we have 2, 3, 1, 4, 1, 0. So this is a 2 by 3 matrix. And so we can multiply it by a 3 by something matrix. And let's make this actually be just a column matrix, which we're going to call a vector. So let's multiply it by a 3 by 1 matrix. And let's make the coefficients be 1, 2, and 1. Then what we're going to get is a 2 by 1 matrix, right? So 2 is going to index this size, and then it's going to be 1. And what are the entries going to be? Well, I'm going to do basically, for the first entry, I'm going to do this, right? So I'm going to get 2 times 1 plus 3 times 2 plus 1 times 1. And here I'm going to get 4 times 1 plus 1 times 2 plus 0 times 1. And so overall, this is going to be 6, 7, 8, 9. And this is going to be 4, 5, 6. So the product of a 2 by 3 matrix with a 3 by 1 matrix is a 2 by 1 matrix, and that's 2 by 1 matrix is going to be 9, 6. And I could have made this 1 by 2 matrix, in which case I just do the same thing over again, and I get another column here. But in particular, this tells you how to evaluate a matrix on a vector, right? Because you can consider a vector as a special case of an n by 1 matrix. Now, the thing is that sometimes we're going to care about inverting matrices. So the property of an inverse matrix is that A inverse is equal to the identity matrix, where the identity matrix is of the form 1s on the diagonal and 0s everywhere else. And I told you before that there's a trick for inverting 2 by 2 matrices. So if we have the matrix A, B, C, D, then I claim that the inverse exists if and only if the determinant is non-zero. And then the inverse is going to be 1 over AD minus BC times you flip the diagonal entries. And then you put a minus sign on the cross diagonal entries. So let's verify that this is the inverse. Should also equal A inverse A. But we're only going to verify one of them. So let's see what happens if we multiply A, B, C, D by 1 over, this is just a number, times this matrix. So this number just comes out front. And let's see what the entries become. So here we get A times D minus B times C. What do we get here? We get A times negative B times plus B times A. So that's a 0, right? What do we get here? We get C times D plus D times negative C. So that's 0 again. And what do we get here? We get negative BC plus AD. And then if we just scale this, we exactly get 1, 0, 0, 1. So that's the general trick for inverting a 2x2 matrix. But there's no such easy formula for inverting 3x3 matrices. And we're in general going to care about that as well. Now I'm going to mention one more thing. Or am I not going to mention? Okay, I'm not going to do a discussion of eigenvalues right now. So I think that's probably going to be it for today. And I swear that I'm now going to work on the assignments. If I'm ending early, okay, so someone raised concerns about whether questions on the assignment were solvable, and I wanted to add one question, and I wanted to add a correction for the x to the x becomes e to the x. And then I owe you notes and I owe you videos. So I will send that out tonight. If I don't send it out tonight, can someone send me an angry email tomorrow saying that I said that I'd do that? I would appreciate that. I'll try and do it tonight. Any questions? By the way, we're doing very well for pace for the material. So literally, what happens is we're going to do linear systems. And then there's a topic on Laplace and Fourier transforms. I technically know a lot about Fourier theory, but I don't know about Fourier theory as it applies to differential equations. So we're going to do Laplace and Fourier theory, and I imagine that's going to occupy like 1 or 2 lectures. And then this is going to occupy 1 lecture. And then we're actually done with all of the methods for solving differential equations that this class involves. And so what's going to happen then for like half of the course is that I'm actually going to have to do a lot more work, and I'm going to have to prepare sections about numerical solutions of differential equations and about applications. So we're actually going to do word problems. I have been doing 0 word problems up to this point. But it's cool because we'll actually going to have done all of the theory about how to actually solve these equations about halfway through the course. So we are like really good for pace. If you look at the course listing, and it has a list of topics, and the list of topics is exactly what I covered. Plus also, well, finishing systems and then Laplace and Fourier transforms. So that's what the rest of the semester is going to look like. Okay, have a nice day.